Alright, time for another DraftPhysics.com, DebatePhysics.com, also video presentation. So, as I have done in the past, I have underestimated the belligerent stupidity of the opposing arguments, the people making those arguments. So, I guess, this is sort of just a key point in physics. I mean, there's just it's really important. If you can't get this right, then really you can't talk about anything, because this is really, the whole story in some respects in terms of what energy, the nature of energy is. And so, as have been often pointed out, okay, I can drop two objects, one from 4 times the height, and or I could just roll objects, do the same experiment by just rolling something on a surface. And if I give this one twice the velocity, okay, one velocity, it does this 4-to-1 thing. And the argument is this is because you can't see that. Oof. And now you can. Close enough anyway. And the simple argument is that all of this does prove, just simple. You can even do it with little rain clouds. The idea that there's a rain falling at a rate, and you're going to go a certain distance, okay, from a house to house. And the idea would be is that traveling that distance, the faster you go across that distance, the less time you'll be in the rain, the less rain you can collect. And so I've used that example of, you could think of this as a bucket, and you could think of this as a bucket, and all it's doing is collecting, okay, an amount of force in the bucket. And so the bigger the mass, the bigger the bucket. And the idea is that as it's always in the same rain, and it just collects it as a force. And so a big bucket falling a short distance, okay, could have the same force as a small bucket falling a longer distance, collecting more rain, getting fuller. Alright, so yeah, it's just obviously, okay, so in gravity, if I drop something, let's just say it falls this distance in 1 second, that just happens to be how it turns out. It'll travel 4.9 meters of distance, and it will be going, when it hits the surface, 9.8. Alright. And then in this case, it's going to do 4.9 here, okay? So everything's working out just fine. It'll be going 9.8 here, and then nothing stays consistent. It won't be going 19.6 here. It won't double. It won't have the same thing happen to it. Whatever happened to it here, by their theory, it won't be happening to it here. Okay, so distance doesn't work. Distance doesn't create the same thing per unit. Alright, but time does, because the truth is this entire process here will take 1 unit of time, and this entire process will take 1 unit of time. So you'll end up with twice the time in the force, and you will in fact hit the ground at 19.6 at velocity, and you will have traveled 19.6 units of distance, 4.9, 4.9, 4.9, 4.9. And you'll weigh twice as much, so you'll take twice the time to do 4 times the distance, and you will have collected twice the velocity, which seems perfectly consistent, and you will weigh twice as much. So it all works, and it doesn't matter which way it's going, right? This stuff is falling with the force, but the force is moving at the speed of light. So obviously the fact that it's going 9.8 meters per second doesn't mean much against 3 million. So the force is clearly very strong. Again, this could be analogized as a stream, your river. And I will pause. Alright, back. So there's a river, and you're going to cross the river, the idea is the simple argument is that it doesn't matter. This distance doesn't make much difference, because if you swim fast, all right, you're going to get pushed to here maybe. But if you swim slowly, okay, then you're going to go right down the river. And that's the truth. And so there's every point in between. The faster you go through the force, the river, the less of it it's going to influence you. The less time it'll have to push you this way. And the more time you spend getting hit by the photons, so to speak, the little bits, the rocks, the water molecules, the fewer of them that hit you, okay, and give you momentum, the less motion in this direction you'll have. So it's, again, you could just make a sun tanning argument. The sun is shining and you're going to move from point A to point B in the field of that pressure of photons. And the simple truth that they're saying isn't true is that if you move quickly through that field, you'll get hit with less photons. And if you move very slowly through that field, you'll get hit with a lot of photons. And if the photons were momentum inducers, that just means you would be bent more, okay, the slower you walk. Now, physics says something really stupid, right? They have a work equation where physicists will actually hold up their briefcase and say, I'm not doing any work, because they're not moving it. Okay. And obviously, to anybody with a little bit of common sense, that doesn't make any sense. Of course you're doing work because you're fighting the stream. You're holding something against the stream. You're doing work all the time. Whether you're moving up or you're moving with the force will change how much work you're doing in any one moment. But the fact is, you're doing work. If I move something into the stream, I can understand. That is, if I try to swim against the stream, I can understand that it's going to be more work, and it's going to be a lot less work if I'm swimming with the stream. But it's still going to do work on me. I'm still going to get pushed. I'm still going to experience the force of the water, but I'm certainly going to experience more of it. I'm fighting it. But it's just about how much time I'm in it. So again, if I can fight it quickly, okay, if I can go very fast, I still get hit by less water, just a fact, and therefore I'm pushed less. So yes, in the suntan argument, I mean, it's just clear, if I stand here and just stand here for 1 hour, I'm going to be constantly hit by the force. I'm going to constantly be collecting its radiation. I'm going to get suntanned. If I go very fast across here, I'm not going to, because I'm going to be hit with less of the substance. And again, you don't have to believe, okay, that gravity is a substance, but it doesn't really matter, as Einstein would say. Einstein admitted that, well, my theory does imply an ether. Whether you call it that or not, it just is implied. You really can't evade that the bent geodesic is using some mechanism to impose the change in the direction. And, you could call it an ether. He was indifferent. He didn't, he was conceding the point that there's a something. There's not a nothing. Nothing doesn't make it happen. So there is something that's making it happen. And again, so whether you believe or don't believe, that part isn't so important. What you think gravity is, the fact that you collect it, the fact that you need to be hit by elements, quanta of it, pieces of it, moments of it, the fact that it is comparable to a stream or to rain or to photons especially. I mean, photons obey the same inverse square law, so you're just basically saying, yes, the radiation is coming out, and what's it doing? Well, it's spreading in 2 dimensions. That's what the square is. Okay, the square is a consequence that the light, okay, the photons are moving away from each other with distance, and they're moving away from each other this way and this way. That's the inverse square rule. And gravity is working the same way. The same kind of rules exist, and so if you travel through any portion of the space that is filled with the gravity, the imbalance, the differential in pressure, That's it. It's going to depend on how fast, how long you're in that amount of that square meter of space that a bunch of energy is going through, and it's just about how long are you going to be in that field differential. Now, some people like to think that all gravity is linear and flat. Well, obviously, a sun, for example, produces a gravity. Like if I put a straight line here, and we call this the sun. Well, you can't see the straight line there. Yeah, I ran out of space. All right. You could understand that any gravitational object has a finite amount of gravity, right? So if I drew a straight line, you could argue that the gravity has a curve something like this. Okay, there's a lot of sunlight here, not too much over here, not too much over here. And what we're really just saying is that if I was going to run across this portion of space through this little vector of space, this cone of space, all right. If I went very fast, I'll be affected by very little. If I run very slowly through that portion, I'm going to get affected a lot. It's just an undeniable argument. The gravity sources are finite, essentially, and that objects can move from one place in space to another place in space and interact with fewer bits from that source. The source is sending them at a constant rate, and all you're really saying is how long am I in that constant rate? Say there's 1,000 photons that go through this space per second. Obviously, the faster I go through the space, the fewer of those I'll get hit by. If I spend 2 seconds, I'm going to get hit by 2,000. If I spend 3 seconds going through, then it's 3,000 of them that will hit me, and I will be changed by them. I'll be obliged to move in a direction because of them. So in every single example, it's demonstrated that it's about how much time you're in the force differential. So I guess that might be too complicated a language. People can't understand that gravity is a force differential. It just has to do with the fact that there's more force in one direction than in another direction. So I could use two objects as an example, a big one and a small one, and you can understand that the little one has little gravity, the big one has lots of gravity, and the force differential, as I move to different locations, I'll have a different force differential, and there'll actually be a place, somewhere around here, where it's the same, where the pulling force, the anti-push in this direction is going to equal the opposite force, and it won't be 9.8 meters per second. There'll be 0 meters per second gravity in that location. And all I do is move to a different place and I change the differential. So whether there's two bodies or one body, there's always just a differential. There's always just saying the 9.8 on the surface of the Earth just means there's 9.8 more going in than coming out. Is the simplest way to understand it. Is that in fact you're standing in a location in space and there's more rain coming down from this side than it's coming up from the other side. Just like in the stream, there's more water going this way than goes this way. So the stream doesn't work very well, just because obviously you could be in an eddy, or where the water is actually going faster this way and it comes back slower this way. But so the analogy breaks down a little bit with rain and water. But that's what you're in. It's a field of force, okay? And it's just about how long, okay, how much of the force you're letting hit you. So, I mean, I've used guns and bullets. You could have a gun firing bullets at a constant rate. And the simple argument is if you go slowly across the distance, you'll get hit with a lot of bullets. You go fast across the distance, only one bullet might hit you. That's simple an argument. It just demonstrates that gravity is a time-dependent force. it doesn't really care about distance. Now there is a correlation. I mean, distance is a symptom of the time, because how much velocity you have will be dependent on how long you were in the force being pushed by it. But that's it. It's just a symptom, okay, of the underlying fact that all it is a force differential, and all that can be argued is how much of that differential did you experience, and that is decided by how much time you were in the difference. Will decide how much velocity you accrue and how much energy you possess. So in the original example, falling, well, I should point out that I have made these arguments over and over again, that you can understand too that even if you're moving with the force, okay, so the force is heading towards the gravitational body, you have a differential of an average differential of say 9.8 through the space you're going to travel. If you go into the space with 500 miles an hour and you travel this same distance, okay, you'll end up going 9.500 and 9.8. Let's just say it takes 1 second to travel this distance at 500 miles an hour. And then I do it by going 10 miles an hour. I start at 10 miles an hour. Well, now I'm going a lot slower, so it's going to take me a lot longer to travel the distance. So now, let's just say it's going to take me 15 seconds to travel the same distance. 15 units of time I will be in the force. Well, now I'm going to collect 15 units of 9.8. All right, so now I'm going, say, 150 miles an hour. So I will have improved my velocity by 140 miles per hour, where all this one got was 9.8 miles per hour. They traveled the same distance, but because one of them traveled it quickly, they got less force. They can't outrun the force. The force is going the speed of light. Again, 3 million miles an hour, 3 million meters a second isn't going to change 9.8 meters per second, that's for sure. Isn't going to mean anything. 9.8 isn't escaping gravity. So they're getting hit by the same force per unit of time, not per unit of distance. And it's only because this was in the gravity longer that it could collect more energy. And it's because this was in the gravity less time, it collected less energy. And so, yes, so now back to the original 4 times the height thing. So that is with gravity. You're falling, free falling in the gravity. Okay. And again, this is all stuff Newton figured out. And the important, I think the really most important features is to recognize that this process, going one velocity here, okay, is going to end up being, well, you're actually landing with one velocity. Let's understand, one velocity when you land. That this entire process, this thing here, the event that takes place here, is exactly the same as this event. These two events are exactly the same outcome, 9.8 meters of velocity. I said 1, but 1 unit of it. Because it takes 1 second. We're saying it takes 1 second to travel that distance. And so in that 1 second they travel 4.9. Both of them do exactly the same thing. This is exactly the same event, essentially, right here. And now we're only going to double the velocity. In the end, we're just going to end up with 19.6. Would it really be realistic for you to say the same event happened here, here, and here, if I only end up with 19.6? And the time, again, this is the same time, 1 second. This will take 1 second. That's just a fact, 1 second. So it's only in the gravity 1 second doing this 3 times the distance. I mean, it's kind of obvious, I think. I mean, only the belligerently stupid would deny, oh, clearly, it only got 9.8. It only moved, it only gained 1 unit of gravitational energy. It got hit with the same amount of force here, okay, that it got hit with in this whole travel, because it moved much faster here, spent less time. So it's the same amount of time, 1 second, 1 second, but time per foot, okay, really changed. The amount of time it spent per unit of distance, okay, kept increasing. And again, Galileo 1, 3, 5, 7, 9, 11, you can just keep doing. It just means 1, 3 over and over again, essentially. It's always going to be this 1 to 3 ratio of accrued velocity. But I mean, this is just the giveaway. This is the same. And then when you roll something, okay, you have exactly, the inverse scenario, okay, where this rolls the one distance, and what's going to be identical with the 2 velocity. You're starting with a 2 velocity. You're not gaining energy now, you're giving it to the ground. And the fact is, you'll give the same amount of energy to the ground in this portion where you're moving very slowly, okay, and you're pushing on the ground more per inch because you're taking your time. You're way more, essentially, and you weighed much less here when you're going fast. So if this was 100 watts, this is 100 watts of energy going into the ground, and this will be exactly the same as this. So 3/4 down the track, you're going half the velocity. Huge giveaway that yes, this is half the energy here was lost, and then you lose the second half here. And it's true no matter what configuration I have this slope in. So I can have the slope in that angle, I can have the slope in this angle, I can have the slope flat. Doesn't matter what slope I push the object against, it's always going to do the same thing, because the friction is being controlled by gravity pushing the object into the surface. And you're going to in fact be hit by less gravity here per foot because you're going much faster through it. So less gravity is going to push you this whole distance, and more gravity is going to hit you here because you're going slower through that distance, much slower. Half the speed, 1/2 the speed here, not here in the middle, here, 3/4. So all these facts point to the force being time dependent. I don't know how else to say it. I mean, it just depends on how long you're in the force differential will decide how much force you're affected by. The longer you're in a force, the more the force affects you. The less time you're in the force, the less the force affects you. That's the elemental reality. And if people can't get that, there's just no evidence. There's just no facts that refute those facts. They're irrefutable facts. There's no experiment, there's no anything that'll indicate that it isn't exactly true. That you can always just figure out how much time was the thing in the force, and it'll always tell you how much energy it could accrue from the force. How much motion. Again, Newton said that force is motion. You want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. Fact. He was correct. That is the reality. Alright, enough said.